Okay, good morning. This is an installment in the 4C conference webinar series. This morning, Koji Ishikawa will be presenting on behalf of Horiba Instruments. I'd like to thank Horiba for their support over many years at the conference and support Koji Ishikawa for the presentations he's done in the past and for today's webinar. Koji, you mentioned you've been with Horiba for about 15 years. Oops, Koji, I'm sorry, you became muted.
All right.
Oh, you unmuted yourself. Okay, so Koji, you've been with Horiba for about 15 years?
Horiba Japan, in Horiba Japan, 15 years, then Horiba Instruments is Houston, 3 years.
3 years, okay,
Yeah.
beautiful. Okay, and again, this webinar is being recorded. It will be available on the YouTube channel for the 4C HSE conference and available on our website. You're free and welcome to share that recording off of the YouTube channel. And without further ado, Koji Ishikawa of Horiba Instruments to talk about real-time analysis of stack gases. Take it away, Koji.
All right. Thank you for introducing myself. So, hello, everybody. My name is Koji Ishikawa. I'm working in the Horiba as R&D for new gas analyzer. So today's my presentation title is real-time analysis of the stack gases. Then this slide shows the objective and the outline of my presentation. Horiba has long history for stack gas measurement in worldwide, and our SEMS analyzer has characterized high sensitivity and long stability using glass flow modulation technology. So today I will explain the feature and concept of N7000 and technology about how we can achieve the high sensitivity and stability. Before I explain the technology, introduce our history of stack gas analyzer. So first, Horiba started to sell the stack gas analyzer in 1967, and Horiba has a long history, almost 50 years. We have developed our analyzer system to meet the demand of the customer requirement. So currently, we ship stack gas analyzer almost 800 units per year in worldwide. Our stack gas analyzer type name is ENDA, E-N-D-A, ENDA. The feature of ENDA series are online and real-time, long-term stability, and high sensitivity. From these features, we provide as a continuous emission monitoring system, it SEMS to customer. Main application is electrical power plant and base incinerator. In this application, for monitoring concentration of exhaust burning gas to ambient, and for controlling plant burning and injection reagent. So this slide explains the product concept of N7000. So 7000 series is the latest product for US market. First concept is performance improvement. I will explain in detail later. Then second one is user interface improvement. And the 7000 has a big screen, 15-inch screen, and simplified menus. And it can remote control. You can check the status and operate by remote, like using a phone or tablet. And next 3 slides, I will explain the 7000 specifications. So this first page is a function of the specification, and the 7000 has a US EPA 40 CFR Part 60 and 75 compliant, and analyzer module to be added when customer need it. And this slide shows the performance of the specification. So 7000 can measure 5 ppm measurement range in minimum, and also total 6 components in one case for measurement. So this picture is the inside of the 90-inch rack analyzer. So each bench is designed compact size. We can make many combinations depending on the customer requirement. That easy can change. Easy can combine some combinations. So from this slide, I will explain our 3 technologies. So first technology, explanation of the cross-flow LDIR modulation. That's measurement components are NOx, SO2, and CO. So generally, non-dispersive infrared, call it NDIR, a lot of components have specific absorbed spectrum in infrared. And absorption intensity depends on concentration. Then NDIR can measure the concentration from this spectrum and intensity. That is general speaking. And also this slide shows the comparison of the non-dispersive IR and dispersive IR. So left side, non-dispersive IR has an optical filter. It can absorb only specific wavelengths. LDIR is suitable for continuous measurement for single component. And right side, the other hand, dispersive IR have grating function. It can absorb wide wavelengths. So our analyzer Ender is selecting a non-dispersive IR type for continuous measurement. Using LDIR and our future technology is cross-flow modulation. Analyzer configuration is one light source, one measurement cell, and detector and solenoid valve. The principle is switching the sample gas and the reference gas at 1 Hz. Then the IR signal is different of the IR absorption between sample and reference. The signal is just absorption different. If change the light source and detector, base 0 is stable. So it's not necessary to adjust of the optical parts, filter, adjustment of a light source. It's not necessary. And clean reference gas is injection to sample cell every 1 second. So it means the cell is always keep clean. This is suitable to measure stack gas continuously. This table shows the comparison table of the cross flow or with non-cross flow. And this slide shows the maximum combination of the LDIR bench. So this bench has only one light source. It's a filament type. And this bench can measure whole components using a beam splitter, NOx, SO2, CO, and CO2. So this bench allows to change the filter according to the component you wanna measure. We can change the detector also. Okay, next second technology is chemiluminescence. Measurement component is NOx and Ammonia. So first, explain the principle. Nitric oxide NO react ozone gas, then nitric oxide oxidize and nitrogen dioxide is generated. A part of generated nitrogen dioxide become excitation states. When nitrogen dioxide change from excitation state to ground state, it becomes luminous like this figure. This emission intensity is proportional to nitric oxide concentration in sample gas. So detector measure the intensity to calculate the nitric oxide concentration. This is the analyzer configuration. So our CLD analyzer in minimum measurement range is 5 ppm. So we are using a vacuum pump. It's kept always minus 9.8 kilopascal, almost 10 kilopascal. And adjust the flow rate at every line, sample line, dilution line, and ozone line. So total flow rate is almost 1 liter per minute. In burning exhaust gas, CO2 concentration is high and change depend on the burning condition. CO2 has an effect in quenching of emission. Then emission intensity is reduced. So our analyzer has a dilution system with dry air, reducing the CO2 quenching. That means our CLD analyzer is stable and no interference in all gas conditions. And using single CLD analyzer and sampling unit, we can measure NOx and ammonia. After sample gas through the primary filter, divide the NOx line and ammonia line. Only ammonia line has an oxidation catalyzer. Ammonia is changed to oxidized to NO, nitric oxide. After that, switching the NOx line and ammonia line by solenoid valve in front of the analyzer. The difference of the NOx concentration is ammonia concentration. So calculation in software continuously. That's measurement of the ammonia. So next technology is a cross-flow ND-UV modulation. So measurement component is SO2. So first, explain the optical characteristic. So light source is used special mercury lamp at the red color, and optical filter at the pink color. It has a center wavelength in 285 nanometer. In this wavelength, NO2 also has absorption. It's a green. When the sample gas is increase the high concentration of NO2, we add the NOx converter in sampling system in order to convert NO. So this is the NDUV analyzer configuration. So this analyzer can measure SO2. Minimum measurement range is 5 ppm. NDUV analyzer also has cross-flow method, and I explained in the LDIR page. It's the same principle, switching sample gas and reference gas by solenoid valve. And in order to reduce the efficiency of the water, PPD tube is existing in front of cell. That purpose is reduce the efficiency of the water. Okay, so next slide, I show the performance results, stack gas. So stack gas analyzer is important to measure continuously. The keyword are stable and sensitivity. About the sensitivity, our technology has cross-flow modulation, and that means I already explained. So next, low sample flow rate. It means improve the sampling unit life. And we made in our facility, our factory, every key parts. HORIBA Japan has making all key parts. So this table shows the result of the repeatability. Every analyzer has a performance within plus minus 0.2% full scale, NOx, SO2, and CO. The measurement range is every 5 ppm. And this is a zero drift result. It shows a result in the weak drift. The average of 3 units in CLD, left bottom, is plus minus 0.7% full scale. And UV, NDUV, upper right, is plus minus 0.3% full scale. CO is plus minus 0.2% full scale. So every analyzer I get result for the stability. So next keyword, what is the sensitivity? So that is the same as ambient analyzer in stack gas measurement. So we modify ambient monitoring technology and eliminate of interference effect and achieve the sensitivity. So these tables are noise level at peak to peak in 5 minutes. Each analyzer are within 1% of full scale. The result is also high stability. And final result is LDL. We have achieved the low detection limit. So, okay, this is my conclusion. Our stack gas analyzer has high performance and user-friendly for operation, and has many functions for stack gas. We are still improving ongoing technology for real-time analysis. Okay, that is my presentation. Thank you for listening. That's it.
Steve, do you want to unmute?
Yes, thank you. Sorry, Todd. I was asking the question, but I was muted. Koji, there's a question, real-time analysis of stack gases. Are there any benefits to bringing in real-time gas composition into a DCS? Koji, are you muted now?
Oh, yes, sorry. Yeah, so our benefit is so real-time measurement for the DCS, right?
Yes, and does HORIBA have its own DAS that's associated with this, or do you partner with other companies that have data acquisition systems?
We have a partnership for the other company.
Okay. So yes, in terms of tying into the DCS, it would depend upon what type of DCS system you are using. If you go to the conference, there's about 5 different data acquisition systems integrators that tie the readings from all of the different DCS or all of the different analyzers, which some of these refineries now have 20 to 50 to 100 different SIMs, and managing the data from those SIMs is quite the task, much bigger task than say 10 or 20 years ago. So 20 years ago, the DAS systems were fairly, well, they were far less sophisticated than they are today. And there's a pretty significant amount of enforcement related to the data acquisition systems and the record keeping and reporting around SIMs. I'd go so far as to say over the first 10 years of the conference, B1, LDIR, tanks, flares, and air permitting accounted for somewhere between 75 and 90% of the violations in the United States. That's why our conference was called LBT in the beginning and then LBTF for LDIR, B1, tanks, and flares. However, over the last year and possibly over the coming few years, issues around data acquisition and issues around SIMs, record keeping and reporting, I believe may become the marquee issue, may become close to the #1 source of violations in the US. So just a little plug there for the conference, managing that data acquisition, and the data acquisition systems have gotten much more sophisticated. The DCS and PI systems have also become far more sophisticated, and I'm referring to just the last 2 to 5 years. So the interaction between those platforms is, well, it may be the #1 issue and the #1 development that is happening in our industry at a compliance level. So the new MAC standards, the RSR standards, the refinery standards, have a much more regulatory, much more complex regulatory approach than say 10 years ago, regarding downtime, what constitutes downtime, all of those issues around calibration. So those are all very significant in our current time frame. And if you work for a refinery or chemical plant and you've not reworked your data acquisition systems in the last 2 to 5 years, I would definitely encourage you to look into that, because the systems available 5 years ago simply were not as robust as the systems available today, and the compliance levels today and the expectations for compliance are related to the massive amount of data around SIMS. The compliance expectations have changed magnificently. So that is a really good question, and you would want to look at the version of the DCS system that you have, because there's the older versions were not as friendly as the newer versions. And what I'm referring to specifically is the ability to interface with DAS and interface with emails and alarms. So the more robust systems now can set constraints, so that as you approach a permit limit or you approach a historical high for that particular parameter, emails can be sent, or other notifications, operator alarms, and all of those things reduce the number of incidents where permit limits may be exceeded. Ned, you have a comment?
Yes, well, I just was wondering here, to what extent can this type of technology, which combines all the different testing methods together, to what extent could that be used on a much broader scale, whereas you're not required to analyze the stacks, but you look at the fence line and for example, refinery as a whole at different points, different altitudes? Is the concentration being so limited that something like this would not work?
Koji, would you like to take the first stab at answering that question? Or I can take a stab at it too, Ned, in terms of...
I couldn't get, sorry.
No, go ahead, Koji, if you have a response.
No, sorry, I couldn't catch, sorry.
You can, okay. Well, there's a lot of fence line monitoring technologies out there. There are many more technologies really coming out, even every day. Just yesterday, I got the email from Koch Industries where they have a technology where they're monitoring throughout the plant. There's many sensors, and you end up where you can hold an iPad and see the concentration at 50 different points across the facility, and based off of the wind, you can triangulate where a new leak has developed, because it's looking at the current concentrations and then changes in concentrations. So in terms of addressing the question of measuring at SIMS versus measuring at fence line versus measuring in the plant, that whole spectrum, of course, that's changing wildly, rapidly over the last 2 years, and far more even over the next 2 years, because of the satellite imagery that can see the concentrations. And the webinar 2 webinars ago talked about the satellites And the satellites, right now, there are only 2 satellites up there. There will be, I think, 5 to 7 within 2 years. So those satellites will be seeing concentrations inside the plant and outside the plant. The fence line monitoring data that's been gathered under RSR, of course, is having an impact. There's the FTIR technology, which is required in California. So they have fence line monitoring using FTIR technology. They have several years worth of data now, many of those systems. And all of those systems are complicated by one issue, which is at a refinery, you have a lot of heaters and boilers with air intakes. So the wind speed and direction, while it may be measured at the fence line or measured at multiple places around the fence line, the wind speed at any given point inside of a refinery or chemical plant will be greatly altered by the air intakes from boilers and heaters. So some of that will also complicate this issue and make these technologies, will challenge some of these technologies. But the question of, more generically, the concentrations of pollutants in and around facilities and the degree to which those are measured, that is changing about as fast as anything in our industry. And there's just, again, a tremendous number of technologies, the satellites, the FLIR camera, a couple of webinars ago, they now have ethylene and ammonia lenses. But again, those would not be seeing the things that this Koji's technology is referring to, because Koji's measuring stacks, and those stack volumes and concentrations are going to be, the stack volumes will be very high, the concentrations will be very low. Optical gas imaging cameras will not be able to see the kinds of concentrations that he's talking about, but measuring after a control device on a stack. And fence line monitoring will also not catch anything from most of the stacks, because the dispersion modeling, the dispersion that impacts from a stack with a high flow rate is going to occur far off property. So that will not be a fence line issue. If anything, it would affect fence line by causing the Venturi effect of pulling pollutants up and into the with the stack, based off the volumes and the velocities around the stack. That's a very long answer to your question.
Okay, thank you.
But of course, your question is a really good question, because this fence line monitoring and the concentrations around the fence line, that for refineries and chemical plants, refineries specifically because the RSR rule, and chemical plants issues vary more. Martin and I were talking about ethylene oxide, and before the conference or webinar started, and the ethylene oxide concentrations, of course, around the fence line that's an emerging issue right now. The webinar, I think 3 or 4 webinars ago, was about ethylene oxide. So for the fence line, concentrations around fence lines of ethylene oxide is a key concern for any sterilization type facilities, but also the 33 ethylene plants in the U.S. Also have that have on their radar this ethylene oxide emerging issue. Okay, here's another question, Koji. If part of the SIM systems has a malfunction, say for one pollutant like ammonia, do you lose air pollutant measurement capability until the monitor is repaired?
Say again, please.
If a part of the system has a malfunction for one pollutant like ammonia, do you lose all pollutant measurement capability until the monitor is repaired?
So our analyzer is maximum 6 component in one 19-inch rack analyzer. If the one component is the problem, so that case, turn off the analyzer, change, replace the module, bench module. But if it's not acceptable for the in maintenance maintenance mode, no stop the measurement. We can build 2 analyzer unit, 2 90-inch rack analyzer module we can build.
Yeah. Oh yeah, I see. Oh, so that's a great feature, really. Because it's modular, you can just swap out the thing that has an issue, and then you can also have a backup to where it can go to the backup if one module of one unit has an issue.
So our analyzer concept is so 6 component in one bench. It's a small. Then that's mean benefit for the customer for the footprint and system space. So this is our concept for the analyzer, 6 component in one bench. But maintenance will be just change the module and do the calibration for the zero and span. That's it.
Yes, perfect. And looks like Lance may have answered that question in the chat line also, if y'all want to see the answer in the chat line. Okay, we have we've gone for about 38 minutes, maybe a couple more minutes. If there are any additional questions. And you talked about sensitivity, Koji.
Yeah.
Would you explain just in general, simple terms, the difference between accuracy and precision and sensitivity and detection limits, which are sometimes, I believe, confused?
So our sensitivity is so measurement range is very low or in the stack gas condition, like SO2 measurement is 5 ppm, but in the stack gas has some interference gas, like methane and the water also. Then our analyzer has a countermeasure for the interference. So that means our analyzer in stack gas has a high sensitivity for measurement.
Okay, so the detection limit is 5, but when you use the word 5, you really mean from 4.85 to 5.05?
Detection limit.
Yes, I'm trying to kind of distinguish between a detection limit and the sensitivity around detection limit.
So our detection limit is so I show the LDL for the presentation.
Yes.
Yeah, so 6 sigma is almost 0.02 ppm. So 5 ppm measurement range and 6 sigma is 0.02 ppm.
Oh, okay. Wow, that's really close then. That's and that's awesome. And you're using the proper language. Okay. Thank you all very much. This will conclude today's webinar. I want to thank you, Koji, for taking your time today, and thank Lance for answering the questions there on the chat line. Thank you, Lance. And thank HORIBA for their support of the conference over the years. We very, very much appreciate your support. The conference, because of COVID, the conference had to be pushed back, and we've had just a really, really heartwarming response from our exhibitors and sponsors, reaching out to us, wanting to do the conference, being supportive and showing their support for the conference. So thank you very much for the very informative presentation webinar today, and also thank you for your support personally, both Stevie, Koji, Lance, all the folks from HORIBA and associated with HORIBA. So thank you all very, very much, and thank you for the attendees at today's meeting. This will conclude today's webinar. Have a wonderful Tuesday. Take care and be safe.